Hello, this lecture is called Matrix Inverses and Systems of Linear Equations. And what we will do now is to learn a methodology to compute inverses of matrices. So we have learned operations, matrix operations, and we learned about addition of matrices, scalar multiplication, scalar multiplied by a matrix. We learned about operators on matrices, like the transposition, the conjugation and transposition. We call that the adjoint. We learned about properties of matrices when considered with inner products, together with inner products. And so one of the operations we learned was to multiply matrices, and we learned this as a new operation, not exactly very trivial, however consistent with linear combinations and with scalar column vector multiplication. So multiplication of matrices is an operation defined in terms of other operations that are standard operating procedure, if you will. So one of the things we learn from multiplication of matrices is that the product of a matrix A times a matrix B is not necessarily equal to B times A. In other words, that when referring to the operation multiplication of matrices, in general, that multiplication is sometimes not true. It's sometimes not true that we can switch the order of the things we're multiplying. The other thing we have to keep in mind when multiplying matrices is the number of rows and number of columns of the matrices we are multiplying, right? So here we have two matrices and they are square matrices, then we expect that the new matrix, the product, is also square. But then we could have scenarios of this type in which we're multiplying a rectangular matrix times another matrix, maybe a square matrix, okay? But there is a requirement that the number of columns of this matrix on the left side of this multiplication, as we call this matrix A, that number of columns has to match the number of rows of the matrix that's on the right side of the product. So there is a requirement in terms of dimensions. That is part of what we learn when discussing, when learning matrix multiplication. So now we're going to refer to the following. We're going to refer to a definition that is in terms of matrix multiplication, and that definition says that if it so happens that you have a product A times B, which is equal to the identity, okay, and you're finding that also B times A is equal to the identity, then in both of these cases, you're assuming that A and B are square matrices, then you would say that the matrix A has an inverse, okay? So you have the matrix A n versus the matrix, and this is a new symbol, A, and then there is an exponent here, -1. This is read A inverse, or inverse of the matrix A, okay? And so we would say that A inverse exists if there is a matrix such that when multiplied by A, that product equals the identity. And so in such case, if A times B equals I, then we would say that in fact that matrix B is the so-called inverse of A. You could also argue that if B times A equals I, then A would be the inverse of B, okay? But here we're defining a new matrix in relation to the operation matrix multiplication, and in relation to that operation, the new matrix is called the inverse of an original matrix. And so now with this definition, we're going to learn how to actually calculate. But what the definition is referring to is that you have a matrix A and a matrix B, and then the product. So what is the product? A times B. Okay, and this is an illustration. That product here We multiply this matrix A times B, right? So here, the first matrix on the left side is A, and this here will be the matrix B. And if we work out this multiplication, matrix multiplication, we find that this is actually the identity, right? So the columns of this matrix product, I'm sorry if you're not seeing B there, so the matrix B, now you can see both A and B. The columns of this matrix product are the so-called standard unit vectors, right? Look at the column 1 here is the vector that has 1, 0, 0, 0, 0, and so on, right? Each of those columns, this column is going to be called E sub 1, this column over there is going to be called E sub 4, right? This is the notation we use for standard unit vectors. The important thing to note here, this is an illustration, is that we are verifying that A times B equals the identity, and in such case we would say that B is the inverse of A, which means that A inverse equals this matrix. So now the inverse of a matrix is a matrix itself, and we would say inverse relative to the operation matrix multiplication. At the same time, this provides an example in which indeed A times B equals the identity, but also, that's what's going on here, B times A. Remember, in general, commutativity is not a free property of matrix multiplication. In general, the product of two matrices is not always the same when you exchange or swap the matrices in the order in which they appear in the multiplication. But in this case, being that one of these matrices is the inverse of the original matrix, then A times its inverse and the inverse times the matrix, they both equal to the same thing, and they both equal to the identity matrix, which is what this illustrates. So what we have in this example is that B is the inverse of A, and that A is the inverse of B, okay? And so one thing to note is that this whole thing is just like the A transpose, which we write A to the T, lowercase, or A to the capital T. Both of these symbols are exactly that, symbols. It's a whole thing. It's not a power, okay? It's a whole symbol. It's the letter denoting the name of the matrix together with that thing that appears there as a super index. And in this case, the super index is -1. So this -1 as a super index of the letter that carries on the name of the matrix that denotes the inverse of the matrix. So far about, as far as calculation is concerned, we can do the calculation of an inverse of a matrix for any dimensions, okay? So if this is something that will apply even when A is n by n, for any given value of n. But in this case, this is illustrated for n equals 5. So we note that the product A times B equals the identity. But now we're going to use this example. In this example, we're going to use A to illustrate a point. Before we were simply using A and B to illustrate that their product equals the identity matrix. But when you're interested in calculating the inverse, suppose now that B is a matrix that you don't know. That's the idea, that A inverse is unknown. Suppose that we don't know what A inverse is, so we need to calculate B. But even though we may not know explicitly what B is, we're going to break this down into a problem here that's familiar to us. Even though we don't know exactly what B is, we do know about properties of A and B, where B is the inverse of A. And that property is exactly this, that in this case is an identity. There's a 5 by 5 rows, 5 columns, right? But we know that A times B, this A times B equals the identity matrix. That we know. Even when B is unknown, we know the product of A times B, whenever B is assumed to be the inverse of A, that product equals the identity. So let's see what appears here on both sides of this equal sign. So on the next line of that this is really a matrix equation. On the left side we have A, B, on the right side we have the identity. So let's examine the left side. This is a column partition, right? If we were dealing with B with n columns, we would have to write more columns. But in this case, we're illustrating this for the case in which B is the inverse of A, is going to have as many columns as A has. So B in column partitioning, assuming that B has columns B1, B2, B3, B4, B5, we write B in this form, and then the product A times B is, this is how we learn to multiply matrices. We think of this product as something that's happening similar to the distributivity property, right? So A multiplies each of those columns, and then you're going to result that the matrix here, A times B on the left side, is a new matrix. Each column of the new matrix is given by the product A times B1. That would be the first column, right? This here is column 1, column column 1 of the matrix AB, and then A times second column B is the second column, A times the third column of B is column 3, and so on, right? And so the important thing is that now, since both sides of this equation, in each side of this equation we have a matrix, then we can equate matrices one column at a time. We can equate matrices one column at a time. So if, for example, take a look at column 1 on the left side versus column 1 on the right side, they are equal because that's what we're applying the knowledge, the information we have at hand. So we would have A B1 equals E1, where E is the first column of the identity. So remember, B1, what is B1? We're assuming that we don't know what B1 is. However, we know A and we know E. I hope this is something that resonates. Second equation leads to A B1 equals E1. Again, B is unknown. However, A is a matrix of constants and E2 is a vector of constants. A B3 equals E3. A would be a matrix of coefficients. And E3 would be a vector of constants. Okay, so these are the things that we do know, and this is now we have 5 vector equations, and each of these vector equations has a vector of unknowns or a vector of variables, right? So B2, B3, B4, B5, and B1, they are the so-called vectors of variables. So what we would do is that we're going to proceed as if this is the one thing that we keep doing and doing and doing, which is solution of systems of linear equations by reduction, by row reduction. So we can think of these problems as problems that involve the matrix A being a matrix of coefficients and the column, the standard unit vectors, the column vectors of the identity matrix as the vectors of constants in the type of problem that we're familiar with, the type of problem that we use row reduction to compute a solution set of a linear system.